Let's take a look at an example problem for ME12 dynamics from our module 10. So in this problem here, we're given an initial diagram where we have a crate here, and we can see with the crate, we have the dimensions of the crate. It's a 1 meter by 1 meter crate. And we can see at a height of 0.8 meters off of the ground, there's an external load of P is equal to 600 newtons. Now they tell us in the problem statement that it's a 50 kilogram crate, so we have the mass of the crate, rests on a horizontal surface, which we have a kinetic friction for, what they give us a mu sub k is equal to 0.2. Now what they want us to do is find the acceleration of the crate if our P is equal to 600 newtons. So now that we've had a chance to read through that problem statement and look at the initial diagram, the next thing we want to do is create our setup page. Now within our setup page, we have a lot of information given to us both in the diagram and in the problem statement. So we can see that our given values here, we have a mass is equal to 50 kilograms. We have a coefficient of kinetic friction, our mu sub k is equal to 0.2, and our external load is equal to 600 newtons. I redraw out my simplified version of my diagram here with the two main dimensions of it, my external load and the distance off the ground here. And they again want us to find the acceleration of the crate. So for our plan of attack, what we're going to do is follow our basic procedure for analysis. Draw out our free body diagram, equations of motion. But one thing that we want to note here is that this load P can cause one of two things to happen. It could cause the crate to either slip or tip. So that's going to be part of the problem that we're going to solve for, is if we push up here at P, does this simply just slide forward, or does it start pivoting here and tip over? So that's something we need to figure out. First, what we need to do is make an assumption and then double check this assumption. So first, as we're solving the problem, let's assume that it slides, and we'll double check this assumption later. For the solution here, recall they gave us a mass. We may need a weight, so we need to multiply through by acceleration due to gravity in order to get this in newtons as a weight. And this is going to be applied at the center of mass. We also want to note that we have a normal force NC that's going to act at a point as well. And point O that we're considering here is going to be some distance from the crate's center line. So we're going to have a center point right here. Again, right there, where again this is going to be the center of mass where the weight is going to act, and then our O is going to be some distance away from this center line based off that center of mass there. Unknown values right now are N sub C, our normal force, our distance x, and our acceleration of g. So what we want to do with this, our first step in our solution, is to create this free body diagram. So we saw that standard procedure for analysis for solving these problems. The first thing we want to do is come up with this free body diagram here. So we have a free body diagram, and we can see now if we take that mass and we multiply acceleration due to gravity, we can get our force here that acts at our center of mass, G here at the center of this. So if we know that this is a 1 meter by 1 meter crate, then this distance from here, the center of the crate, to the end of the crate here is going to be 0.5. We're going to have some point here at the corner that we're going to call A here. I'm going to establish a coordinate system. We'll call X positive going to the right, Y positive going up, and if this is moving to the right, I'm going to say that my A sub G, my acceleration over the center of gravity here of the crate, is going to be moving to the right. Other things I know, we know that this right here was 0.8 meters off the ground. Well, the center of this is at 0.5 meters, so this is another 0.3 meters above the center of this here, and this is going to become important when we're talking about the slip or tip criteria for the crate when we apply this load now at 0.3 meters above the center line right there. We also know we have a frictional force here opposing our direction of motion. This is equal to F of equal to mu sub k times our normal force N sub C. Now our N sub C is going to be acting at some point O right here, a distance of x away from our center line. So there's our N sub C, our normal force. So again, frictional force is our coefficient of friction times that normal force. Our normal force is some distance x away from our center axis. Again, we know that center axis from the edge of the block is 0.5 because the whole block is 1. So a lot going on here, and you can see it gets messy quickly. So as we switch over to my next slide here, I'm going to redo this out by drawing it within PowerPoint rather than doing it by hand, just so it's easier to follow along. We don't lose anything within a complicated diagram. So that's what I do here. I redraw this out in PowerPoint just so it's a little bit neater and easier for me to reference back to, or somebody else to follow my work as compared to my hand drawing of my free body diagram, because what I'm going to be doing next is deriving my equations of motion from this free body diagram. So I want to make sure it's neat and clear so I can reference back to it and get everything correct. So I look at this here, I have my given coordinate system that I've chosen up here, y positive up, x positive to the right, and I have my acceleration to the right, which is going in the direction of motion there. Now down here to my free body diagram, I can have my weight acting at my center of mass here of 490.5 newtons. I have my external load P over here coming in at a distance of 0.8 meters above the ground, which is 0.3 meters above our center line right here, and our center line is 0.5 off the ground right there because our total height of our box is 1 meter. Now I also see over here I have my frictional force, my F, and this is equal to my mu sub k, which is given as 0.2, and my normal force N sub c. And my frictional force is going to oppose the direction of motion, so my frictional force is acting in my negative y direction here because my direction of motion is going in the positive x direction. I'm sorry, negative x direction because my direction of motion is moving in the positive x direction here. Now I also know I have my N sub c. My N sub c is going to be acting at point O on our crate here, where my point O is some distance x off of my center line. So I can also see that my center line is 0.5 meters away from the edge, or my point A over here, where our point A is going to become important when we're talking about the tip or slip criteria right there. So I have a lot of information here. I have my weight force, my external force P, and my normal force and my frictional force right there, and all the associated dimensions and locations of those. So that's going to be very important as I start out by creating my equations of motion. So the first thing I want to do is separate them out. Three different things. We have my summation of forces in the x direction, summation of forces in the y direction, and my summation of moments about g. So let's start with our summation of forces in the x direction. We have x positive going to the right over here. So what forces are acting in the x direction? Well, I have my P force, and I have my frictional force here, where my P force here is acting in the positive x direction, so that's 600 meters acting in the positive direction right there. Then I have my frictional force acting in the negative x direction, so I have a negative 0.2 NC going in my negative x direction. This is equal to the right-hand side of Newton's second law, F is equal to ma, is my mass times acceleration. My mass is given to me here as 50 kilograms, and my acceleration is my a sub g that I'm looking for. So this gives me my first equation from my free body diagram. So now that I've done it for my x direction, I want to find my equation of motion now for my y direction. So I can reference back to my free body diagram over here. Again, I know my coordinate system that my y is positive up, negative down. So I can see I have in my y direction for forces, I have my weight force acting in the negative y direction here, and I have my normal force opposing that acting in the positive y direction. So I draw out my second equation of motion, summation of forces in the y direction. Well, I have my positive normal force minus my weight force, and it's not moving at all in the y direction, so that's equal to 0 there. So I have my N sub c minus 490.5 for my weight force is equal to 0. So the last thing that I want to do now is talk about this third equation of motion here, because if you see here I have an a sub g and an N sub c up here that I don't know. I can solve for my N sub c here. So I can use these in order to solve for my a sub g based upon my N sub c, but then I'm also going to need to come down here and solve for my other unknown, my third unknown, x. So three unknowns, x, N sub c, a sub g. I need three equations of motion here. So this is my third equation, summation of moments about my center of mass here, my g. So what is going to create a moment about my center of mass? Well, I have this external load P here times this distance of 0.3 here, and that's going to be going clockwise around that there. So this is going to be a negative. So I use my right hand rule when I come around here. If it's going clockwise, my thumb's going in the negative direction there. So this is a negative. So I draw this out right here. If I'm going clockwise, a negative moment from 600 times my 0.3 right there from this external load P at this distance of 0.3 meters. Then I take a look and say, okay, well, I'm also going to have a moment about g from this N sub c times this distance x. I use my right hand rule again. I can see my thumbs coming back out of the board here. So therefore, this is going to be moving counterclockwise in our positive x direction from our right hand rule there. And lastly, I have one more force that's going to contribute to my moment about G, and that is this frictional force right here. And we can see that is going to be this frictional force times this distance of 0.5 right there. Again, do my right hand rule, that's going into the board there, so it's going to be negative for my frictional force, which is 0.2 NC times that distance of 0.5. So this gives me now my third equation here from my summation of moments for my third equation of motion, where again my unknowns in here are my N sub C and my X. So now that we've got three equations and three unknowns, we can solve them simultaneously. Now this is something we could do by hand. We could plug this into Excel. We could plug this into MATLAB, Python, Script. There's all types of way numerical solvers to solve simultaneous equations. But this one's pretty straightforward. And what we can note is right here from equation number 2, there's only one unknown. So we can solve this directly, and we can even do this pretty much in our head. But I would encourage you to write it out in case you drop a negative or anything, so somebody can follow your work. That our N sub C is going to be equal to 490.5. So our normal force acting at some point C down here is equal to 490.5. So now that I have that there, I write that out from equation 2. Here's my equation 2. I can derive that N sub C is equal to 490.5 newtons by simply taking and adding this 495 to both sides over here, moving it to, over to the right, and we end up with our N sub C. Now, if we take this N sub C here, we can go back into equation 1. If we were to plug in for N sub C, that's our one of the two unknowns, so our only unknown that would be left would our A sub G. So if we plug in our value for N sub C into equation 1, we end up with a 600 minus 0.2, plug in our N sub C of 490.5 is equal to 50 times A sub G. Do out the math here, we end up with 600 minus 98.1 is equal to 50 AG. Do our subtraction, 501.9 is equal to 50 AG. Rearrange and solve for AG. A sub G is equal to 501.9 divided by 50. And now I'm doing a little bit of unit analysis. So again, as I'm plugging these into each other, I want to make sure this is an acceleration. Do I have the right units for acceleration? Did I do my math right? Did I plug in correctly? So I plug in my units here. This is in kilogram meters per second squared. This is in kilograms. The kilograms cancel out. And what I end up with is A sub G is equal to 10 units of meters per second squared, and that is correct. Those are the units for acceleration that I would expect. So now as we continue on with our solution, I copy over my three equations that I derived from my free body diagram, my three equations of motion here. And it's really nice that we label these, because now I can reference back to them as equation 1, equation 2, and equation 3, and that becomes important in these multi-step problems here, where now I can simply say, okay, I'm going to plug my value for N sub C into equation 3. I can reference back over here, oh, that's my equation 3, and this is my N sub C that I solve for numerically by solving my equation number 2. So I take this value for N sub C and I plug it into equation 3 wherever there's an N sub C. So I have an N sub C there and an N sub C there. I can plug in. So I now end up with negative 600 times 0.3 times now my N sub C of 490.5 times X minus 0.2 times my N sub C times 0.5 is equal to 0. Simplify this down, 600 times 0.3 negative is negative 180. This is still 490.5 times X. Combine these and I end up with negative 49.05 is equal to 0. Combine like terms here, my negative 180 and my negative 49.05, I can both move over to the right-hand side of the equation, add those together, and it's 229.05 is equal to 490.5x. I'm solving for x. I rearrange, solve for my x. 229.05 divided by my 490.5 will give me a value now for my x. So now I've solved for all three of my unknown variables. I have my N sub C, I have my A sub G, and I have now my x value here. And what the x value is going to do for us is it locates our normal force based upon our center of mass of our crate, which also lets us know if it's slipping or tipping. So because our x value is 0.4675, and this is less than that 0.5, which is the distance from the edge of the crate to the center of the mass there, we assumed correctly in our assumption that this was going to slide. Now, if this x had lined outside of that area there, if it was greater than our 0.5, the problem would have to be reworked with the assumption that slipping was going to, or the tipping was going to occur rather than the slipping that we assumed. So based upon that assumption, we lucked out and we don't have to resolve the problem. If this had been greater, we would have to stop, go back now, and resolve the problem with tipping occurring.